Another example to try to figure out what does its end behavior look like. Well, I have a function written, but it's kind of disguised because it's not specifically in the standard polynomial function form. It's a product rather than a collection of cascading terms. It's a product of terms. So how do we determine what the leading coefficient is? Because that's what we're looking for. The leading coefficient determine end behavior. Well, you need to use your imagination a little bit here and imagine, well, if we multiplied all these terms out, what would the leading coefficient be? And basically that's what happens when I multiply that term by that term by that term. I have, in this first one, I have an x cubed term. In the second factor, x minus 1 squared, that produces an x squared term. And in this last one, I just have an x to the first term. All those terms are going to be multiplied, which will produce my highest leading coefficient, which will be an x to the sixth term. Now, you may not believe me, and if you don't believe me, that's fine. Then what you will need to do is go through and go back and multiply those three terms together. And then you'll discover, well, yeah, that does make sense. The leading term is the first term times the x, or the x terms times the x terms times the x terms. And notice that this x squared, it came from this x minus 1, but the entire term is being squared. So again, if we multiply that out, that would get me an x squared term. Now the way to look at it too is you just want to add up all the indexes of all the x's. X cubed plus an x squared plus an x produces x to the sixth. All right, that was maybe way over explaining what we're doing, but our goal is to determine what's the leading coefficient of that function. Because once we determine the leading coefficient, then we can determine what is its end behavior. So we know that our leading coefficient is negative. So we know that we're going to have a graph that tends downwards on both sides, and it's x to the sixth, which is an even number. So let me back on up. So we know it's an even, so it's going to be one of these two. Our leading coefficient is negative, so it's going to be more similar to this last graph, where its end behavior with values extremely negative are decreasing, and values of x that are extremely large are also decreasing. So the end behavior on both of these, on this particular function, mimics a little bit with this one in some type of way, where its end behavior starts off with low values, and on the negative x side, and on the positive side, it also ends with decreasing values. I think that's probably the best way to say that.